Welcome everyone. This is separation processes course. Our topic today is multi-stage, multi-component distillation. So we are still talking about distillation, which is a separation technique based on the difference in boiling point temperatures between the light component and the heavier components. And we are still talking about a multi-stage. So it's like we are having a column, and inside this column there are many trays or stages. But now the new term here is multi-components. Actually, it is not very new term because we discussed it before, the single stage multi-component distillation. If you remember before in the previous videos, we talked about the single stage where only we have one stage and we have a feed that contains many components, 1, 2, 3, 4, 5, and these components are being distilled using a single stage. Yeah, this was in the previous videos. uh, so our topic today is the same thing, multi-component. So we don't have two components binary system. Now we are dealing with a mixture, more than two components. It could be 3 components, 4 components, etc. But it is not a single stage, it is a multi-stage. So it's like we have a column, and this column contains several stages, trees, and again we have a condenser and the boiler and the feed. But the feed is not only 2 component, but it could be 3 or more. Yeah, 3 or more, 3, 4, etc. So this is what we mean by a multi-component. So again, the topic is multi-stage, multi-components distillation. So this is multi-stage, many stages, and this is multi-component. We have more than one component in the feed. And this is distillation, which is a separation technique based on the difference in boiling point between the components that are to be separated. Okay. So before we start discussing this analytically, there's a very important point that you need to notice here, that in order to be able to apply graphical solution like makeup tele method or Ponchon Sabarite method, etc., it is only valid if you have binary mixture, C1 and C2, 2 components only. If you have more than 2 components, you cannot rely on graphical solution. Why? Because graphical solution is two-dimensional. It's only two-dimensional solution, so it's only applicable if you have 2 components. When you have 3 component, 4, 5, so you are going with higher dimensions, 3, 4, 5, which difficult to draw or sometimes impossible to draw. So we cannot rely on the graphical solution for multi-component. So what do we need is to get some equations that help us to do the same calculation that we have did for the binary mixture, but not using graphs but using equations. And these are usually not analytical equations, they are numerical equations, that equation that gives some approximates, that gives some estimates of the required parameter, like the minimum reflux ratio, the minimum number of stages, and the actual number of stages. Yeah. So rather than determining the stages using graphical solution, no, we are going to use equations to determine this number of stages for multi-component. But the question here, can we use this equation for multi-components for 2 components only? The answer is yes. Why not? Why not to use them for 2 components? It's okay. You can use this equation also to get an approximate solution for binary mixture. it's okay, there is no problem. But you cannot use graphical methods to get solution for multi-component distillation. Okay, so again, you cannot use graphical methods to get a solution for multi-component distillation, but you can use it only for the two components. But when it comes to the equations that you are using to predict the number of stages for the multi-component, you can use them also if you have only two components. Nothing prevent you. Okay, it is all about the accuracy. Okay, so at the end of the day, both with a graphical solution or this equation that I'm going to present today, both are just numerical approximate solutions. They are not exact analytical solutions. Okay, so before we start, let's take some of the terminologies out of the way. Like, for example, there's something we call fractional conversion. The fractional, not fractional conversion, sorry, it has to do with the reactor. It's called the fractional recovery. Fractional recovery. What do you mean by recovery or fractional recovery? It is like the amount that you recover either in the distillate or in the waste. So it is like if you have this your distillation column, this is your feed, and with a composition of the light component ZF, and then this is the top product, the bottom product. Of course, here we have a condenser and the boiler. Just assume they are all reside in this beautiful rectangle. Okay, so we have the top product and the bottom product. This is D with XD, and this is waste with X waste. Okay, so what do you mean by fractional recovery? Uh, Fractional recovery, it is a fraction, and when we say a fraction, it means it is between 0 and 1. It's a fraction, fractional recovery. What do we mean by recovery is the amount that we recover. For example, if we say the fractional recovery of a component I in the distillate, so simply we are referring to the amount that we recovered in the distillate with respect to the feed. So it is simply what we recovered in the distillate, which is XDI distillate over the original feed, which is ZFI multiplied by F. So it is like the composition of component I in the distillate multiplied by the distillate flow rate over the composition of the same component I in the feed multiplied by the total feed flow rate. And so that's what mean by the fractional recovery in the distillate. Similarly, the fractional recovery of component I but in the waste, again same idea. What we recovered in the waste, X waste of component I multiplied by the total flow rate of the waste over the composition of this component I in the feed multiplied by the total feed flow rate. So that's what we mean by the fractional recovery. And of course that you can say with confidence that the fractional recovery of any component I in the distillate, what we recover in distillate of component I plus what we recover of component I in the waste is equal to 1. Why? Because if we have a feed with a specific component I, okay, of course this we are assuming steady state process, so nothing will be accumulated inside the column. So whatever we are feeding of this component I, well, partial of it will be recovered in the distillate, especially if it is a light component, and the other partial of this will be recovered in the waste. So the summation of this fractional recoveries will be 1. It is like when you say summation of mole fractions is equal to 1. Okay, because nothing will accumulate inside the column. So what you recover in the distillate plus what you recover in the waste will be equal to unity, 1. Okay, and when you have when we said before, we have a binary mixture. For a binary mixture, it is like we having only two components, for example, A and B. One of these components is the light, the light component, and the other will be, of course, the heavy component, and it all depends on the boiling point. Which of these components has a lower boiling point will be the light component, and the one that has a higher boiling point will be the heavy component. Okay, so this is for the binary mixture. But when it comes for a multi-component mixture, and let me draw it in this way. Example, suppose you have this one. This is the condenser. Okay, and this is the deboiler, and this is your feed. So you have a feed with composition in the feed, and you have a distillate with a composition in the distillate, and you have a waste with composition of the waste. What happens is that when you have a multi-component, it's like you having in the feed, you don't have only this two heavy and light, but you have for example component A and component B and component C and component D. Okay, and for example, suppose we have this component A, B, C, D. Okay, so we don't have only one light component and one heavy component. So what we do is that we focus our attention on two components only, which are the components of the interest, and we call them the key components. The key components. Okay? So, for example, suppose here the components of interest are the components of interest, for example, let's say they are B and C. Okay, they are B and C. So we will call them key components. We will call them key components. Okay, and one of these key components, these two, will be lighter than the other one. It all depends on the boiling point. Or in other words, it depends on the relative volatility. Okay, so the one that has a higher relative volatility will be the light component. Okay, and of course this relative volatility need to be referred to one of these components, and usually it is referred to the heavy key component. And what do we mean by heavy key component? So let's take it step by step. The first thing is that our focus or interest will be on the two components. One of these will be lighter than the other. So the lighter one, we will call it, for example, if it is B, we will call it light key, LK, LK, light key. So it is a key component and it's light. The other one, we'll call it HK, heavy key. So it's a key component and it is heavy. The others, which is in this case A and D, we'll call them uh, non-key, non-key components. So we are not interested in them that much. Okay, and if this non-key components are lighter than the light key, we can call them LNK, light non-key, light non-key. Similarly for D, if it is non-key and it is heavier than the heavy key, so we can call it HNK, heavy non-key, heavy non-key. Okay, so what's the criteria to determine which one is the light key and which one is the heavy key? Okay, it is all based on which two components we are given information for. Okay, So for example, if we are given the fractional recovery of B and fractional recovery of C, so this means that B and C are the component of interest. Or for example, if we are given the composition of B in the distillate and the composition of C in the waste, so in other words, they are the components of interest, so they are the key components. Okay, and remember that the relative volatility of any component I, k, is equal to distribution coefficient of this component I, okay, over the distribution coefficient of the heavy component. Okay, in other words, you cannot only say it is alpha I, it's better to call it alpha I j. That means the relative volatility of component I with respect to component j. So usually component I could be any component, which is A, B, C, D, but this j component, which we are calculating this relative volatility based on it, it is usually uh, the heavy key. Yeah, this is the heavy key. So in this case, it is C component. So we can say that alpha A, for example, will be nothing but Ka over Kc, and again alpha B as Kb over Kc, and alpha C is Kc over Kc, which is 1, right? And similarly alpha D is Kd over Kc. So these are the relative volatilities with respect to the heavy component, which is C in this case. Okay, so the higher the relative volatility is, this means this component is light. The lower the relative volatility is, this means that this component is heavy. Okay, so back to our example. Suppose that uh, suppose that C is our heavy component, B is our light key. So if A is lighter than B, in other words, A has a higher relative volatility compared to B, so we are going to assume that everything that's above the light key will be drawn totally at the distillate. Nothing of this A will be found in the waste. Okay, so this is just an assumption which is valid. Okay, and the other assumption is that we are going to assume that if we have anything that is heavier than the the heavy key component, so for example if it has a relative volatility that's lower than the relative volatility of the heavy component, heavy key, so we are going to assume that everything that is heavier than the heavy key will be drawn only as a waste product, and it will never found in the distillate. Okay, then based on this assumption, this light key and heavy key will be distributed on both the distillate and the waste. They will be distributed in both. Okay, so it is like we are referring back to the binary mixture some way. We are referring to the binary mixture as a part of the multi-component mixture. So we are referring to the binary mixture as the light key and heavy key component, and the other will be either totally drawn at the distillate or totally drawn at the waste. But this light key and heavy key will be distributed partially in the distillate and the waste. And of course, the light key will occur more in the distillate, while the heavy key will occur more in the waste. Okay. So yeah. Okay. So Okay, so let's make to make our life easier. We are going to introduce some new symbols. They are just as simple. So we are going to refer to the light key as I, and they are just as simple, just as simple. And the heavy key we are going to refer it to as J, and the non key, whether it is a heavy non key or light non key, I'm going to refer them to as a key. Okay, and the composition in the distillate of any component I multiplied by the distillate flow rate, we are going to refer it to as dr. Okay, this is just as simple. Okay, and the gain, which I refer to the molar flow rate of individual component I in the distillate. Again, anything at the waste, composition of the waste of any component I multiplied by the waste flow rate, we are going to refer it as Wi, which is again the total flow rate of the waste multiplied by composition at the waste of a component I will be the molar flow rate of component I at this waste. Okay, and again we are going to refer to the composition of the feed component, the composition of any component I at the feed multiplied by the total flow rate of the feed. We will refer to it as this f small I. So it is the flow rate of component I in the feed. Okay. Uh, so you can simply say that the distillate is nothing but the summation of dr. The summation of all individual component flow rate gives you the total flow rate of the distillate. And again, you can say that the feed is equal to summation of Fi. The summation of all this small Fi, the individual component flow rate of the feed, are equal to the total feed flow rate. And similarly, the waste be equal to the summation of Wi. Okay, so the total flow rate of the waste is equal to the summation of individual flow rates of individual components and the flow rate and the flow rate of the waste. So yeah, just symbols. And actually, there is an important point that I would like to refer here is that, as you know, in this column, we have a different temperature. We have a temperature in the feed, and we have a temperature in the distillate, and we have a temperature in the waste, and of course the temperature at the waste we have this reboiler, so of course it will be much higher than the temperature in the feed where there is no reboiler, and let alone that the temperature of the distillate will be much lower because of presence of this condenser that's cooling. Okay, so as you can see we have a different temperatures across the column. So somehow the value of relative volatility is just a property, so in other words it depends on the temperature. So it is like you have a different temperature at the waste, at the feed, at the distillate. At these different temperatures you have different relative volatilities. Okay, and usually we like to deal with the average relative volatility. And how we are going to get this average relative volatility? Suppose in an average relative volatility is a simple relative volatility average of any component I. Of course, this with respect to the heavy component, as we mentioned before. Uh, so this relative volatility, if it is not averaged, you need to average it. Okay, based on the relative volatility in the distillate, in the waste, and in the feed at different temperatures. And how we can average them? We can simply use what we call geometric average. Yeah, geometric average. It's like, you mean there's mainly there are three types of average. We have an arithmetic average, and you have geometric average. You have a geometric average, and you have a, uh, uh, log. Logarithmic average. Logarithmic average. And you have a, uh, uh, log. Logarithmic average. And you have a, uh, uh, log. Logarithmic average. And you have a, uh, uh, log. Logarithmic average. And you have a, uh, uh, log. Logarithmic average. And you have a, mean average, or log mean, or log average. Okay, so the arithmetic average, when you say arithmetic average, like you are finding the average as x1 plus x2 plus etc. up to xn over n, right? Or summation of different values over their number. So for example, it could be x1 plus x2 over 2, or x1 plus x2 plus x3 over 3, etc. So this is what we call arithmetic average. Okay, and you have a log mean average. Log mean average is like if you want to find the average log mean. So what you do is that x2 minus x1 over len x2 over x1. It is like it's commonly used in the delta T log mean in heat transfer. So you say it's delta T2 minus delta T1 over len delta T2 over delta T1. So it's just a way to find the average. Okay. The third way is the what our concern is the geometric average. And what do we mean by geometric average? Of course, it's nothing new. I'm sure that you studied it in high school. But just to remind ourselves, and geometric average, it is like if you want to find the average, geometric average, you take this root. For example, if you have 2, so it would be x1 multiplied by x2, then you take square root. If you have a 3, x1 multiplied by x2 multiplied by x3, then you take cubic root, etc. If you have 4, you take a root to the power 4. It's not a power actually. It's like this in this index of the root. Okay, so you get the idea. And as you have many values here, you are increasing this index for the root. Okay, this is what we call a geometric average. Okay, and this is what you are going to use if we would like to average this alpha. So you can average this alpha relative volatility of any component I simply if you have, for example, if you have the relative volatility of this component at the feed and the relative volatility of this component at the distillate and the relative volatility of this component at the waste, so you multiply them and then you write here the root, cubic root. It has an index of 3. Suppose you don't have information, for example, supposing you don't have information about the relative volatility at the feed. So what you do is rather than cubic square root or cubic root, it will be just a normal square root. Okay, so it will be square root because you have only 2 values. Okay, so that's what you call the geometric average, and it's usually used to obtain an average value for the relative volatility that we are going to use it in the calculations. So now I think we are ready to move to the calculations. As we say, the multi-component, multi-stage distillation cannot use a graphical solution. We are going to rely on equations, and these equations, we have many sets of equations. One of the sets that what we call a method called FUG. It's called FUG method. FUG method. And what do we mean by FUG method? These are names of the 3 scientists who work together in order to develop this method, which is of course it's approximate method, it's a numerical method. It is not that much accurate, but it is good enough for design calculations and rough estimation. And yeah, so what do I mean by FUG? F refers to Fenske. This one is Fenske. U refers to Underwood. G refers to Gilliland. Fenske, Underwood, Gilliland correlation. It's a correlation called FUG, Fenske, Underwood, Gilliland. And this Fenske, Underwood, Gilliland are just three three equations mainly. Yeah, I can say three. Yeah, mainly three types of equations. The first type of equation, that's called Fenske equation, are used to get the n minimum. The n minimum, the minimum number of stages. The U Underwood is the set of equations that are used to get the R minimum. Last thing, that's Gilliland, is a set of equations that are used to get the actual number of states. So you don't need to use any graphs here. You don't need to draw any graphical solution. You are going to determine the number of stages. So it is not like before where you use this and then you start counting number of stages. No, no, just using equations. And in order to get this number of stages, you need to move in this path. You need first to determine the minimum number of stages, then you determine the minimum flux ratio. Then with the help of these two informations, you can use Gilliland correlation to get this total number of theoretical stages. Okay, so again it depends on the value of n minimum and r minimum. You cannot move and get this n from Gilliland before you get this two. That's why it is called FUG. Okay, so let's start with the first thing here, what we call the Fenske. Let's start with Fenske. Let's start with Fenske equation. So what's Fenske equation? Fenske equation, as we agreed, it's used to get the minimum number of stages, and minimum, it is like the ratio of two lens. We have a len here, and we have a len down here. So at the denominator, it is just the len, yeah, len average, len of the relative volatility, average relative volatility of the light key. Okay, and this one that's above, or let me call it, as we agree that the light key is, we give it a symbol as I. That's to make simple more simpler. So when I say I, it is same as light key, as we agreed before. I is light key. And here inside this len, we have x d of the distillate of I light key over x waste of I light key divided by x d of j, and we agree that j refers to the heavy key. J is heavy key over x waste of, again, g, which is the heavy key. So this equation is used to determine the minimum number of stages. And you can see that this equation could be written in a different form. If you let us take, for example, actually it is a powerful way to rewrite this equation in another form. You can use this form, or there is another form. So let us take this part. So we have, if I take this part and I write it as this, it is x di over x dj. Okay, x di over, and this denominator of denominator would be a numerator, so it is x wj over x wi. So a good point to notice here is that if you multiply both the numerator and denominator by the distillate, and if you multiply again both numerator and denominator by the waste, what you get is that, what's this? dx di. It is just di, right? Which is the composition, which is the flow rate of the component I, light K, and the distillate. Okay, and again, what's this? X dj. It is just dj, the flow rate and the distillate of heavy K. And what's this? Waste fill X du. It is just wg, the waste flow rate of heavy K, G. And what's this? xwi في w, this is wi, the flow rate of the I, which is the light key, and the waste. So an alternative way is to write this term instead of this term, and here you can remove this and write it as di multiplied by wj over dj multiplied by wi. So it depends on the given information and the problem. Whether you have the compositions, or you can shift this equation or this relation as flow rates. So it depends on the given information. So this is another way to express this equation, because I find it helpful in some questions. Okay. So suppose, yeah. Yeah, I think that's it for the Fenske equation. This is what? Yeah, I think this is enough for Fenske equation. And now let's talk about the Underwood equations. And yeah, Underwood equations. These equations, again, as we agreed, are used to determine the minimum. Are used to determine the minimum reflux ratio. Are used to determine the minimum reflux ratio. Okay, and how to determine this minimum reflux ratio? We know that the reflux ratio itself is L over D, if I'm not mistaken. Yeah, L over D. This is the reflux ratio. So if you want to find the minimum reflux ratio, so you need to use the minimum liquid flow rate inside the column. Okay? And of course, if this L minimum, if this L changes to this L minimum, this will be directly changed. How? How? Because they are related through material balance in this relation. L minimum يساوي equal to V minimum minus distillate. Okay? It comes from the fact that if you have, where's the column? Yeah. So we have here vapor going up. This is a vapor, and here we have this, the distillate, and this is liquid going down from here. So you can see that the vapor is equal to the liquid plus D. V is equal to L plus D. Okay. So yeah, V is equal to L plus D. So you can rearrange equation as L is equal to V minus D, or L minimum is equal to V minimum minus D. So if this L changed to L minimum and this V changed to the V minimum, this D will automatically change. That's why I'm just saying that R minimum is equal to L minimum over D. Okay, so you can see that in order to get this L minimum, you need to get L minimum and D. And how to get this D? It's a simple material balance, as exactly same as we discussed before. It is you are making a simple material balance around the whole column. around the whole column. Okay, so this is your control volume. So you can, it's like as previous, exactly as previous. You will say that F is equal to D plus W, and then ZF of component I, F is equal to XDI for D plus XWI for W. Okay, so you have two unknowns, D and W. You can solve for them if you know this XDI and XWI. Only you know the percentage recoveries. So this is a way to get this D. Another way, if you know the fractional recovery of a component in the distillate. So as we discussed before, what is the fractional recovery? Yeah, this is the fractional recovery. If you know this fractional recovery, and you know the feed and composition in the feed and XDI, you can solve for this D. Okay, so you can use the fractional recovery to get this D. Uh, yeah. Uh, okay, so you can get this D easily, but the problem here is how to get this L minimum. In order to get this L minimum, our target, we need this L minimum. Question here, how we can get this L minimum? So simply, L minimum is for material balance, as we discussed, it is V minimum minus D. So D can easily get. Question here, how we are going to get this V minimum? How to get this V minimum? Here we need to seek help from the Underwood equation. So we have a set of equations called the Underwood equation. The first equation is called the first Underwood equation, and the second one is called the second Underwood equation. Before we discuss the first Underwood equation, let's start from the back. Let's start from the bottom, from the second Underwood equation. So what's the second Underwood equation? This second Underwood equation is this equation. The minimum V that we want, remember that we want this V minimum, because if we know V minimum, we can get L minimum. If we know L minimum, we can get R minimum. Okay, so keep this in your mind. That's why we need this V minimum. So V minimum, the second Underwood equation says that this V minimum is just the summation of this relative volatility of any component I. So please don't be confused here when I say summation of component I. It's a summation. It is a summation. Like, I'm going to repeat this term many times. It's like when we say summation of xi is equal to x1 plus x2 plus etc, x3 plus x4, etc. So when I write this summation here, I'm referring to a repeated term, and when I say I, this I is for any random component. It's going to be repeated for all components. Okay, so it will be alpha 1. Or let's stick with the same symbols. We are using A, B, C, D as a multi-component mixture. So this alpha I will be alpha A, then alpha B, then alpha C, then alpha D. So it's a summation. So it is not this I here, it is not the light key. Okay, so it will be summation of this alpha I multiplied by di, and remember this di is just the xdi multiplied by the total distance. Okay, so we can say it is just simply di, okay, over what, over again alpha I, that the volatility of component I, minus a new term here. Let me do it in different color. A new term here called capital phi. This capital phi. Okay. So you can see here, if we know the relative volatility and we know the individual flow rate, or we can calculate it, of the components in the distillate, we can get this V minimum. But before we can get it, we need to somehow to find this capital phi value, this tall phi. Okay, the question here is that how we can get this phi value, how we can get this phi value, from where we are going to get it. So we need the help of the first Underwood equation. We seek a help from the first Underwood equation that help us to determine this value of phi. Okay, that's why I started in vice versa. I start from the second Underwood equation, then I'm going all the way back to the first Underwood equation. Okay, so what's the first Underwood equation? It says that 1 minus q. And what's this q? It is exactly the same as previous q that we tend to use, which is the percentage of the liquid in the mixture. Again, it is 0 for saturated vapor, it is 1 for saturated liquid, it's between 0 and 1 for saturated mixture. It is above 1 if it is subcooled, if it's below 0 if it's superheated. Okay, so it's again the same q. Okay, 1 minus q is equal to summation again of alpha I. Again, this I is for the summation, it is not for the light K. Alpha I Zi over alpha I minus eta, or phi. Okay, so as you know that this value of Q is known from the state of the feed, whether it's saturated liquid, saturated vapor, etc. So you know this, and this alpha you can know it is a property, and usually the composition in the feed for all components are given, so you can solve this equation to get a value of phi using a solver. Okay, but the problem here is that this equation this phi has many solutions, and the solution that you are going to get depends on your initial guess. So you need to choose a good initial guess for this phi value, and the good initial guess needs to be, so this is just a guess, a good initial guess before you use your solver. You need a good initial guess, and this good initial guess lies between the relative volatility of the heavy key and the relative volatility of the light key. So for example, if this is 2 and this is 1, so a good initial guess would be 1.5, 1.4, 1.7, etc. Okay, then you use your solver in order to determine this phi. Once you get this phi, you put it here in order to get V minimum. Once you get this V minimum, okay, go back. Once you get this V minimum, you can get N minimum. Once you get this N minimum, you can get R minimum. That's it. And once you get the R minimum, this is our target. Okay, so yeah, that's it. That's it for the Underwood equation. Now the third thing is the Gilliland equation, which is used to determine. So the third thing is the Gilliland equation, which is used to determine the actual theoretical number of stages. I would say not actual, it's theoretical number of stages n, which we tend to use to determine before using a graph. If you remember, we use this graph and then we count number of stages. This was before. Now we can apply this Gilliland correlation in order to get this n. And how to get this? Of course, so far, So far you have n minimum from Fenske, and you have r minimum from Underwood, and you can get, of course, r. It depends on the like, for example, sometimes they say for you that r is equal to 1.5 r minimum, for example, or whatever, 1.6, 1.7. So if you know r minimum, you can get r. So I am assuming that you know this r at the end of the day. So you know n minimum from Vensky, you know r minimum from Underwood. This r can be determined, so you know it. So how to get this n using Gilliland correlation? The first thing that you do is you find the value of something called just a random variable that we call it x, and we say this x is just r minus r minimum over r plus 1. So if you know r minimum from Underwood, you know r from whatever relation given in the question, you can determine this random variable that's called x. And once you get this x, you can determine another random variable called y. And how you are going to determine this? You would say that y is just 1 minus exponential of this thing. 1 minus exponential 1 plus 54.4 x over 11 plus 117.2x multiply by x minus 1 over x power half. X power half, yeah, this is half. So that's it. You plug in the value of x, you get the value of y. But again, the question here, why we are doing this? Why we are getting this value of y? What's the benefit of getting this value of y? The benefit is this. If you know y, you can use this Gilliland correlation, which said that y is n minus n minimum over n plus 1. So you can see here, if you know n minimum from Fenske and you know y from what we did before, you can use your solver to get the value of n, which is the theoretical number of stages that you are looking for. So that's it. Congratulations, you got the number of stages without the graphs and without all of this. But this again is just approximate solution. Even the graphical solution is approximate solution. Okay, if you want a very accurate solution that's it's not analytical but very close to the analytical solution, you need to use software like Aspen Hysys, for example. And this is just an elementary calculation. It's good enough for design purposes and optimization. Yeah, so that's it. You get this in. Suppose you are interested to get the feed location, the feed stage. In order to get this feed stage, you can apply a beautiful equation called the Kirkbride equation. And what's this Kirkbride equation? This Kirkbride equation says that, of course, let's agree on something, that for your distillation column, as we agreed before, we can split this column into a rectification. If this is your feed, you can into the rectification section and stripping section. So in the rectification section we have some stages. Let's call them NR, stages in the rectification section. And in this stripping section we have some stages. Let's call them NS, stripping stages. Okay. So Kirkbride equation is as follow. It says that the number of stages in the rectification section over number of stages in the stripping section is equal to something big to the power 0.206. 0.206. Okay, and yeah, inside this square brackets we have the feed the feed composition of the heavy key over the feed composition of the light key, then you multiply it by this rounded brackets squared, and inside it is x waist over xd, but x waist of what? Of the light key, and xd of what? Of the heavy key. This is heavy key. So again it is xw of the light key over xd of the heavy key. This is heavy key, all squared. Then you multiply it by w over d. And as we agreed, this w and d could be obtained either from the fractional recoveries or from the overall material balance. So you got this w over d. So this equation tells you that if you know w from material balance, for example, overall material balance or fractional recoveries, and you know d, you know xw of your light key, or you can get it somehow. You know xd of the heavy key, or you can get it somehow. You know the feed compositions of the light key and heavy key. If you know all of this, you can get this ratio nr over ns. But the question here, this is only one equation, and we have here two unknowns, nr and ns. So how come we can get the value of these two unknowns using one equation? In other words, we need to seek a help from another equation. So we have two unknowns, two equations, and the second equation will be n equal nr plus ns. The total number of stages on the whole column is equal to number of stages in the rectification section plus number of stages in the stripping section. Okay, so you know this n from where? From Gilliland. From Gilliland correlation, you know this n. Okay, and once you know this n, you have these two unknowns, nr and ns. Two unknowns, two equations, you can solve them simultaneously. Okay, you can solve them simultaneously in order to get nr and ns. So suppose, for example, if you get nr, for example, don't know, for example, you get it approximately 12. Let's say ns is equal to 6. Okay, and you are counting stages up to down. So you have this, just to make life easy, let's say 3 only. So we have 3 stages at the rectification. So this is 1, 2, 3. Then stripping stages are 6. 1, 2, 3, 4, 5, 6. Okay. So the feed stage will be somewhere. The feed stage will be somewhere in between the rectification section and stripping section. So for example, you can say it is stage number 3 or stage number 4, or between 3. Of course, there is no feed between two plates. Should be either plate 3 or plate 4. And at the end of the day, they are just approximate solutions. They are just approximate. So you can say approximate it is, for example, stage 3. More prefer, يعني, usually you are getting fractions. So if you get this nr as, for example, 3.9, so you can say it is stage 4. So it is just an approximate solution, whether stage 3 or stage 4. Yeah, this will be your feed stage. So for example, you can say for this question, your feed stage will be stage number 3, yeah, for example. Okay, so that's it. This is FUG correlation, Fenske, Underwood, Gilliland correlation that are used Again, Fenske used to determine the end minimum, Underwood used to determine R minimum, Gilliland used to determine the theoretical number of stages, and this is an approximate solution using numerical correlations in order to get the total number of stages that are valid. Again, remember this FUG are valid for multi-components, multi-components. Also it is valid for binary, because binary mixture is a special case of multi-component. Okay, so they are valid for both. They are valid for both, and they are called the shortcut methods for analyzing distillation column. So that's it. Thank you for your listening, and I wish you all the best.